If you have watched the previous videos in this series, you know about dichotomous data, you know about a Bernoulli event, you know about joint Bernoulli events, and you know about the binomial coefficient. We can now wrap this all together to construct a probability distribution known as the binomial distribution. It is a probability distribution for dichotomous data. As with the construction of any distribution, we have some conditions that we have to meet in order to create the distribution. First, we're going to make n observations based upon drawing a sample from a population, and for each of these n observations, we're going to categorize using dichotomous categorization. That is, we're going to categorize every observation as a success or as a failure. Each observation that we obtain must be independent of the other observations. We cannot take groups of observations that come together as a cluster, but rather we must sample independently from our population. And then the probability of success must stay constant. That is, if there is anything that might influence the probability of success, that influencing factor is not going to take place during the time of our study, during the time in which we make our individual observations of members of the sample drawn from the population. Now, how does this tie into how we conduct our research? First, we have to identify the target population, that is, the population of individuals we're interested in, and that almost always goes beyond a population that we have access to. So we have some subset of this target population that I call the accessible population that we actually can draw our sample from. We are hopeful that the accessible population represents the target population, but if it does not, it would be good to identify the characteristics of the accessible population so that we know what part of the target population we are studying. Then we must randomly sample n participants from that accessible population, again making sure that these are sampled in a way that each individual member selected for our study is independent of the other members. We're not going to pull out, for example, an entire class of students as the members of our sample because we would expect those students to be related by the fact that they are in the same class. We want to take each observation independently of the others and make independent observations that allow us to categorize each participant. So when we are deeming whether a participant was successful or whether a participant failed in the task, we again want to do that in a way that that observation doesn't influence the observation we make of other participants. The fact that we want the probability to stay constant may be a bit concerning. You may ask yourself, if I were to take n observations from a population, why would I expect the probability of success to be the same for every member of the population? For instance, let's suppose that success is passing a test. Certainly, we don't expect the probability of a pass from one student to be the same as the probability of a pass for another student. So let's think about that for a moment. Here we have a population. Let's suppose that the proportion of individuals who are going to pass the test or be successful in some other way is symbolized as pi. We draw a participant at random and categorize that participant as successful or as having failed the task. What is the probability that that individual will succeed? That probability, you may notice, is closely tied to our sampling. That is, if there is a certain proportion of individuals in our population who will pass the exam, then when we randomly sample, the chance of us obtaining one of those individuals is based upon pi, the proportion that will pass. So you can think of the probability of an individual passing an exam is the probability that I will select an individual who passed an exam. So when you hear us talking about the probability of the treatment being successful, in research terms, you can consider that as the probability that we will select an individual for whom the treatment will be deemed successful. This should ease your mind about keeping the probability of success constant, because that probability is based upon random selection from a population. It is not based upon every single member of the population having the same probability of success. We have learned that if we have a series of Bernoulli events, that as long as they're independent of each other, we can calculate the probability of the joint Bernoulli events. For example, let's suppose we have a population in which 70% of the members of the population will be successful. We now randomly choose our sample, say 4 members of the population, and then we categorize each one of these as being successful or having failed. Let's suppose again that it is taking a test, and we have 3 individuals that pass and 1 individual that fails the test. What is the probability that this will happen? If we have chosen these individuals independently, we know that all we have to do is multiply together the individual probabilities, like this: 0.7 times 0.7 times 0.3 times 0.7, and that yields 0.1029. So the probability of this particular sequence of Bernoulli events is 0.1029, or about 10%. In general, the probability is pi, our proportion in the population that will be successful, raised to the x power, where x is the number of successes, multiplied by the probability that a person drawn from the population will fail, that would be 1 minus the probability of passing, raised to the power of the number of failures. Well, if x is the number of passes, n minus x is the number of failures. But notice something. This probability calculation, this product, is based upon this specific sequence. And in earlier videos, we talked about the fact that we don't really care whether it's the first person that passed and the third person that failed, or the other way around. So let's go back to the probability of 0.7. Assume we make 4 observations, and now all we're interested in is what is the probability that 3 will pass and 1 will fail. Not that the first, second, and fourth will pass and the third will fail, but that 3 will pass regardless of which 3, and 1 will fail. Now we can bring in the binomial coefficient, and we have 4 choose 3 times 0.7 raised to 3, that is 0.7, the probability of passing, and 3 being the number of passes, times 0.3, the probability of selecting someone who will fail the exam, raised to 1, the number of failures. That yields 4 times 0.1029, or 0.41. So whereas the particular sequence of the first 2 and fourth passing and the third one failing had a probability of 10%, if we don't care where that 1 failure occurs, we just want to know the probability of 3 passing and 1 failing, then we have 0.41, or about 41% of this event occurring. We can write it like this. The probability of capital X equaling little x means the probability that x, that is the random variable of the number of successes, equals some specific value of x, such as in our last example we used 3 for the specific value of x. That's equal to, and now we have the calculation for figuring out the binomial probability of 3 successes and 1 failure, or whatever in general you want to put in for x. to see that number of successes out of n trials. We're finally ready to construct a probability distribution, and this distribution is known as the binomial distribution. Here's what we do. We set a fixed probability of success. In our previous example, we set that to be 0.7. Now we calculate the probability of a certain number of successes, we call x, in n trials, but we do it for 0 successes, 1 success, 2 successes, all the way up to n, so everyone is successful out of n trials. That collection of probabilities forms a binomial distribution for x successes in n trials when the probability of success is denoted as pi. So here is the binomial distribution for the example that I just showed you. What I have done is use this binomial formula to calculate the probability that we would have 0 successes out of 4 trials, and you can see a little small bar indicating that it's a small probability. The probability that we would have 1 success out of 4 trials, a little bit higher. The probability of 2 successes out of 4 trials, higher still. The probability of 3 successes out of 4 trials, that's the highest, and that should not surprise you, because if the probability is 0.7 and 3 out of 4 is 0.75, it should not surprise you that our largest bar here is 3 successes out of 4 trials, and now the probability dips a little if we talk about all 4 of the members of our sample being successful. What would we get if we added up the probability denoted by the height of each bar? Let me stop, see if you can get it. If you said 1 or 100%, you would be right. Why? Because we have a complete, exhaustive list of possible outcomes. These possibilities are what we call mutually exclusive. That is, you're either going to have 0, 1, 2, 3, or 4 successes. You're not going to have all of those at the same time or 2 of those at the same time. It's going to be one of those. So these are mutually exclusive events, and it's exhaustive. Something here has to happen. We either have to have 0 successes or 1 success or 2 successes or 3 successes or 4 successes. One of these things has to happen. So basically, we have looked through the entire space of our possibilities. And so if we add this all up together, it should be 100%, meaning one of these things is going to happen. In your life with traditional statistics before entering the nonparametric statistics domain, you frequently worked with the normal distribution. The normal distribution is a distribution out of a complete family of distributions that we could call the normal distributions. Well, now we're dealing with the binomial distributions. Let's compare. The normal distribution assumes that our response variable is continuous. It can range anything from negative infinity to positive infinity. The binomial distribution assumes we have discrete data, data in which you can only have 0 to n successes, where n is the total sample size. The normal distribution is a mathematical model that we use to approximate the data. Our data are never going to be actually normally distributed. We just hope it's close enough. By contrast, the binomial distribution is an exact distribution. It is literally constructed based upon the real possible outcomes that we can achieve in terms of the number of successes when we make n observations. A specific normal distribution is identified by its mean and standard deviation. A specific binomial distribution is identified by the probability of success, pi, and the sample size, n. So while the parameters of the normal distribution are mu, the mean, and sigma, the standard deviation, The parameters of the binomial distribution are pi, the probability of success, and n, the sample size. The normal distribution can be used to approximate a probability. The binomial distribution can be used to provide exact probabilities. In summary, the binomial probability distribution provides the probability of observing x successes for a fixed probability of success for each of n Bernoulli events, that is, observations that yield dichotomous data that we generally call success or failure. The probability of success can be hypothesized and tested with exact probabilities using a binomial distribution, just like we can conduct a test of the mean using the normal distribution if we assume we have a normal distribution of data. The probability of success can be hypothesized multiple times in order to construct a confidence interval for the probability of success. These last two bullets suggest what's coming next in this series, where we're going to test a hypothesis using the binomial distribution, and then we're going to construct a confidence interval using the binomial distribution.